All right, guys, let's get started. So this section has a few things. And really this is a lot of this is a hodgepodge of like algebra 2 trig honors, right? And stuff you guys did in the fall last year or of the previous school year. So real zeros of polynomial functions, sketchy polynomial functions, intermediate value theorem we'll talk about. Remainder factor theorems we won't get to today. Because that involves a bit more like that's an extension of synthetic and polynomial division, which I'll talk about that, but not going to do the extensions of that until Friday. So the real zeros, remember, there's a few ways you could say it. So when you say what's the zero of a function, you can say what's the zero of a function. They'll say it's a solution of a function. They'll say x minus a factor. You say a conjugate and x intercept. So a lot of the ways you can express the zeros or the solutions to an equation, they're all interchangeable terms. So if you said, what is the solution to this equation? Yeah, great. This is zero. It means that y equals zero. That's what we call a zero. Or it says an x intercept. Great. It's an x intercept. Or x minus that number is a factor. Cool. But they all work. All very interchangeable terms. Extrema, we do care about too. Extrema are extremes, high points and low points, right? So if your degree is n, there's at most n minus 1 local extrema, at most n real zeros. And the word at most I emphasize. So what if you have like y equals x to the 4 power? Clearly the degree is 4, right? But if I graph it, how many extrema does it have? How many low points does it have, or high points? Just one, right? Just be that, right? But this is a little wackier. I'm totally making so I don't know if this is going to work. I'm just totally making this up. But like, what if I have something like this here? I think it's going to be kind of wavy like this. No, I lied. It'll be kind of more like this. Again, I don't know if this works. I'm just totally guessing. But how many extrema does this have? 3, right? Peaks and valleys. This is what note that. A few valleys and 1 peak. 1, 2, 3. We have at most 3. How much is crossing that fact? 4. So not a guarantee. They have 4 real zeros in the degree is 4, but you can. That's a possibility. Now, this right here, x to the 4 power, just has 1 x intercept, but it has a degree of 4, or has a multiplicity of 4. So it's actually 0 shows up 4 times if you think about it. But sometimes graphs could look like this, right? Degree 4 functions. Very possible we can get this here. If I have 2 x intercepts, right? The other 2 zeros are not real anymore. The other 2 zeros are what? Imagine they're complex. Exactly. We're going to talk about it later on. For sure. There's a complex. Oddly, you don't deal with any complex numbers in AP Calculus AB or BC. It has like 0 place. Don't know why we do it all the time here, though. I don't know. But anyway, just so you know, that's what's happening. Okay. So here, determine the zeros of this. What is the maximum number of local extrema it can have? Well, it can have 2 local extrema. That's obvious. Because your degree is 3, right? Now, factor, what can I factor out? X. You get 3x squared minus 5x minus 2. Now, however you go about factoring a quadratic, totally fine with whatever you guys do. If it's my Algebra 2 class, I do take a somewhat more rudimentary approach. You guys, if you just want to just do trial and error, totally cool. But sometimes I do this if I get really confused. I'm not sure if you guys have ever done that, like the diamond. Have you guys done that before? Yeah, then I do this box thing, or factor by grouping. I'm not sure if you guys have seen this before. If you want to do it, you can go ahead. But I'm going to put negative 6x and negative and positive x. So I split the middle term as negative 6 and 1, because negative 5x is the middle term, so negative 6x and x is splitting it. I should have 3x coming out here, x, negative 2, positive 1. Yeah, I should get 3x plus 1 and 3x. No, 3x minus 2. Does that make sense? I put it in the wrong place. You are 100% correct. Yeah, guys, I know how to factor, right? No. Okay. Yeah, it's x minus 2. My bad. X minus 2. 3x plus 1. Yeah, I'm correct. There we go. Honestly, whatever you do the factor, I'm cool. I'm cool with it. Totally cool with it. Okay. Okie dokie. We're cool. We're good. Okay. Awesome. And by the way, for local extrema, to find them exactly, you're not going to learn how to do that until we've actually done some calculus. And even then, I don't know if we'll quite do that kind of calculus until you guys do AP Calculus A, B, or B, C in the fall. But you'll really start learning that process in the spring. So for now, you're going to have to just use Desmos to find the local extrema, like just or TIA4 calculator. But you will learn how to find it analytically once you've learned some calculus. Okay. Oh, what the question want? They want the zeros, right? Where are the zeros here? Yeah, easy. Okay. Okay, let's move on. Okay, multiplicity when the zeros are repeated. So if k is even, the graph just touches the x-axis, doesn't cross it, it touches it, and then goes up in the other direction, right? So a good example would be something like this. Let's say you have y equals x minus 2 squared. So it just touches at x equals 2 and curls back up. Easy peasy. Not hard. And the sign stays positive either side. If it's odd, if you have an odd function, let's say you have y equals x minus 4 cubed. 1, 2, 3, 4. The graph will look kind of like this. It passes through, right? So y has a change sign on either side. So no sign change. For y here, sign change for y there. So actually, I'm gonna get this pretty quickly. Okay. Good. We're okay. Yeah. All right. Great. Easy peasy. All right. Now the homework. Actually, I do want to give you guys enough time to work on homework today because we have 75-minute classes. You know, it's a long class, and some of the homework problems are like this, right? If you look at the homework for tonight, same instructions, right? Same instructions, and 6 times, but it's good because you guys need it. So I'm going to model it for this problem here. Just we'll kind of go through this kind of quickly. Degree of 6. Do you guys see why? Why is my degree 6? 1 plus 2 plus 3, right? Oh my goodness. You guys are so much better than me. Why did I say 6? What mistake did I make? What did I assume was there that's not there? I assumed there was an X next to that. I'll be honest. That's I'm serious. I know that. Okay. Yes, it's 5. My apologies. Find all the real zeros. Yeah, that's easy. That's 2 and -3. The 2 has a multiplicity that's twice. -3 is 3 times. Or if you want to use thrice, if you want to be kind of cool that way. 3 times. Determine the graphs and behavior using limit notation. Okay, well, your leading coefficient is negative, right? Your degree, of course, is 5. So you got a negative leading coefficient. You got an odd degree. Remember, the arrow is going to look like this when that happens. The arrow is going to look like that. How are we going to write this? Now, I'm going to force you guys to write it this way now because we are doing calculus in 2 or 3 months from now. So I'm going to force you to write it like this. For the left arrow, you can say limit x approaches negative infinity, f of x equals, we'll have a blank here, limit as x approaches positive infinity, f of x should be equals, not colon, my bad, equals blank. So this is for the left arrow. This is for the right arrow. Because think about it. If that's an approach to negative infinity, you're at the left. If that's to positive infinity, you're at the right. Well, the left arrow is pointing up. So what are we going to say? And pointing down for the right arrow, we're going to say, done. There we go. Just visualize it, right? Not hard. Positive infinity, negative infinity. Now, there's 4 scenarios only, obviously, right? Because you have 2 things you're answering, and each thing you're answering has 2 options. So there's 4 possibilities. How did I know the left arrow was up and the right arrow was down? Just use logic, right? Like we thought. With a negative coefficient, right? The negative 5x and 5 is going to dominate, right? But a negative leading coefficient, that's going to dominate that term. Well, if I put in a negative number for x, because we're going towards negative infinity, if I put in negative 1,000, right? Negative 1,000, which is this power, is still negative. But then times a negative 5, it's positive. So that's what's positive. And hot, right? If I put in a positive for x, let's say 1,000, right? 1,000 for x. 1,000 difference is positive, but then you will find negative 5, it's negative. So if you think of it like that, you'll be fine. If you have even degrees, of course, arrows go in the same direction. Positive pointing up, negative pointing down. And of course, if I have a positive leading coefficient with odd degree, it's reversed, down, then up. So, okay, so that's done. So A, B, C, D, all done. Sketch the graph. Okay, let's do the graph. And then what is the maximum number? Well, I know that's going to be 4. That's easy, right? Okay, let me go and clear the screen for now. So I need some space. So I'm going to do some tick marks. 1, 2, 3, 4. 1, 2. I just feel like doing 4. So x-intercepts are good, right? The y-intercept, forget it. I mean, I'll find it, but it's just going to be so hard to plot. But I'll find it. End behavior again. We know is this, right? Sign chart. So if I start with by plugging a value bigger than 2, like say I plug in 3, negative 5 times a positive is negative. Are we going to see a sign change at 2? Because it's squared. No. Are we going to see a sign change at negative 3? Yeah. So my sign chart should look like this. Okay. I have 2 x-intercepts again, 2 and negative 3. Right? We know this already. And behavior, we know this. I know the arrow is going to kind of look like this, right? I expect this. The y-intercept's kind of good, just to verify that you've done everything correctly. I think it's going to be negative 540, if I'm not mistaken. Am I correct in saying that? 0 minus 2 is negative 2 squared is 4. 4 times negative 5 is negative 20. 3 cubes 27. Yeah, I got it. Negative 540. Okay. So it's way down here somewhere, right? So let me get rid of the arrows because they're just a little off. But it's going to look like this, right? We're going to pass here. And we're going to touch this, come back up, and bounce there. And there's a graph. It's negative 540. Now, do I know the true lowest point? Not really. I mean, I kind of made one stuff, but I don't know the lowest point. But I have to go and count this. This is probably the highest point. You're not breaking. Touching, not breaking. So I'm pretty sure that's been the highest point for that part, the local extrema. And why do we say local? How come I don't say absolute?
I mean, it's higher in the second one. There. So
yeah, I don't know where it is. It goes up forever. I don't know where it's the lowest one. So if we call it local, there's a couple ways to look at it. The rudimentary way, which is not the best way, but you can think like in this kind of vicinity, it seems like it's kind of the highest. Like I'll give you a good example, like if you look at home prices, like locally in Redwood City, what's probably the most expensive house, maybe $4 or $5 million. But absolute in the Bay Area, probably 50 million, nothing but expensive. So I don't know, it's kind of crazy. So, but it's really, what's the best way to think about it? Increase, decrease. You have a local max, just when you switch from increase to decrease. Because increasing is the y is increasing when x is increasing. When x is getting bigger, what's y doing? An increase in x causes y to go up. That's an increase. It's like a roller coaster, right? Before the roller coaster off to the left, going down to us. We're going up here. So yeah, we're definitely seeing a positive change in y, for sure. But there's a switch, and when that switches, that's a local max. Now down here, that's a local max. That's a local max. Why? Because we're going from decrease to increase. Going down, then up, down, then up. So we call that a local max. Now we have to look at too, which we'll talk more about with the Precalculus. So another thing about too. You do it tangentially. Or tangentially is a line that grades the ground, right? Just touch up. That's what's positive. That's what's negative. That's a derivative by the slopes of these lines are called derivatives. If that's positive, that's negative, and we see a switch there at this peak, or at this extreme, we call it a local mass. So we call it a local number. Absolute means when you have a set domain, closed domain, and what's the highest and lowest in that closed domain, then yeah, then you can talk about absolute and maxes. Or it just happened to be the highest point.
Just both arrows point down, then sure. You could say absolute. So, all right, anyway, let's try this again. Why don't you guys try this one on your own? I will do it. I'll freeze the screen. We'll check in about 2 or 3 minutes, okay? Try one on your own. Or check the table mates, that's fine too. Thrice. It's a double negative, dude. It's double negative. It's like when someone said I didn't do nothing, like they did something then. If my kids say that, it's like he did something. Or me, myself, and I. You're right. Wait, I made a mistake somewhere. Hold on. Yeah, I made a mistake, guys. I goofed. Thank you, Kath, for correcting me. Here we go. My bad. Thank you. Is that correct now? Yeah.
Yeah.
Yes, there we go. Oh, yeah, yeah, that was. I had the way.
Before, yeah.
See, you're not.
Okay, sorry, I had it wrong initially. So this helps a lot. I was just busy these, listening to your guys' conversation. I was distracted. Yeah.
So there's a balance of 4. I did a sign chart. The sign chart confirms that. All other x-intercepts, we see a sign change. Yeah, and the arrows both point up, so we're good. Okay. Let's now move on to page 3. All right, guys, quiet down, please. Thank you. All right, intermediate value theorem. This is actually covered in calculus as well. If you wind up doing AP Calculus AB, it's covered usually in the first unit. And I think I'll bring it back when we start talking about calculus in the spring. It's pretty simple. Let me do a diagram first. The diagram I think helps. Reading the words sounds confusing. Let's do the diagram first. I think that'll help. And let me actually make up numbers here. Let's say it's like 1, and 4. And say it's like 2 and 5. Okay, so I made up some numbers.
Let's say A is 1 and B is 4. Let's say F of A is 2 and F of B is 5. So here's the thing in the graph. If we here work intermediate, you can go in between, right? Like for example, intermediate level something in the middle, right? Or actually, let's listen to this podcast about part 30. I think that would be six. That's a high. I know I'm a lot, but this is it's a great podcast. It's an NFL record for like highest efficiency for intermediate classes in 20 yards. So anyway, point being, intermediate is in between. So, right, okay, sorry, getting a little too crazy about football, but intermediate is in between. So here's the deal: if X is between 1 and 4, will there be a Y value between 2 and 5? Yeah. If X is between 1 and 4, there will be a Y value between 2 and 5. At least once. At least once will happen. So that's what this is saying here. If the function is continuous, are there any breaks here? No. I do a nice smooth curve, right? Nice smooth curve from A to B. Actually, these have to be smooth. There can be some like corners too, like some ragged edges. That's fine too. As long as no breaks. And also, we assume that these are not the same. That should have the Y coordinates are different between 5 for X equals A and X equals B. And in this interval, F takes on every value between F and F B. Every value between 2 and 5 can be F. At least once. So any Y value between 2 and 5 is valid. As long as your F is between 1 and 4. That's all saying.
So that's what's happening there. Questions? Before we do the example. So anything between 1 and 4 for X, the Y value will be between 2 and 5. And every value between 2 and 5 can be had as long as your X is between 1 and 4. So can Y be 4.999? Sure, totally. Can Y be 2.001? Sure. As long as X is between 1 and 4 in that interval. So you have to be continuous, and also has to be a closed interval too, just so you know. Has to be inclusive. Very important. Because here's the deal. If you're not continuous, just doing, you don't have to do the sketch, but if you're not continuous, if you have a break here, right? Are all Y values covered between A and B? No, because there's a break, right? So that's not possible. Or if you're not continuous, sorry, if you're not closed, if you're not closed, then I don't, then you're not going to have something at X equals B. So here's a good question. Do go ahead.
So you had like the A and B X values you picked like right before and right after. Like the Y values would go above like the range like A.
That's fine, but anything between the two Y values for the X endpoints.
So like, I know what you're saying. You're saying yes, like this here. I think it's a thing of it. It's like this, is that what you're saying?
Yeah.
Yeah. So any Y value between these two can be had.
Yeah.
That's also. So any between A and B, there'll be a Y value now.
It doesn't have to be.
No, not necessarily. But yeah, but any Y value can be had. Right. So like for example, if I choose like this is 1, 4, right? At X equals 2. I mean, yes, obviously it's up here, but definitely anything in between these two, I can have a Y value. You can make all. Right, I can make all Y values happen. Totally. Yeah.
Okay, go ahead. No, it is inclusive of F and F of B.
Okay.
It is. No, it is. Oh, it's inclusive. Yes, 100%. I don't know why. Yeah, it shouldn't. Yeah, it's so Y is totally going to be in between F of A and F of B, inclusive. Totally. Yeah. So here's a good extension of this, and it's a little confusing at first, but they're saying use the intermediate value to show that this has at least 1 0 in the interval from 0 to 1. So when you have a 0, that means Y equals 0, right? So 0. So what the question is really asking you, does this equation have a solution? Yes or no? That's what it's asking you. The answer is yes. First off, why is it yes? Is this continuous? It's a polynomial, sure. Is your interval closed? Yeah, because what's our interval? 0 to 1, inclusive, right? So here's what you do now. You do f of 0. What's f of 0 going to be? What's f of 1 going to be? Careful. 4. So here's what now you make a statement by IVT. F of x will equal 0 at least once. You know, let me type it up. That's gonna be better. So basically what you do is you tell me if it's continuous, tell me if the interval is closed, plug in the values, f of 0 and f of 1, and you make a statement. Here's a statement, I'll type it up. By IVT, f of x equals 0 at least once because f of x is continuous on the closed interval and I need to make one more statement at least once on the interval. There we go.
You don't have to say exactly that way, like you could rearrange it, you could say, hey, since f of 0 is less than or less than f1, and we have a, fx continues on closed intervals, then we know that fx equals at least 1 students at IVT. Like you can reverse the wording, you don't have to say exactly this way, but it's gotta be something like, you got to be IVT, you got to understand this closed interval part, you got to tell me what's going on here. You have to.
You don't have to like give it continuous.
Yeah, you don't have to prove, I mean, yeah, just make the statement. I mean, we know it is as a polynomial function, but you don't have to prove it.
There is a way to prove continuity as we get to calculus. We'll talk more about that later, but yeah, just say it because it's a polynomial function. So, okay, that's IVT. That's it. That's all there is to it. And that's an example how you would see it. Okay, polynomial long divisions, not my favorite, but we'll do it. In this case, we have to do polynomial long division because you're divided by non-linear. So must do this if dividing by a non-linear expression. And clear x squared plus 1 is not linear, so we just gotta do it. We'll do it. And yes, this will play a role in calculus. It actually comes back with a vengeance, calculus. So not until probably spring, I think, for both AB or BC. So you guys remember how to do this? What do you multiply x squared to get to x cubed? And then you multiply this by x, right? Does that make sense what I'm doing? Okay. Hope that makes sense. So that cancels. You bring this down. That cancels. You bring down the -3. Now, what do you multiply x squared to get -3x squared? -3. So you multiply x squared plus 1 with that. Oh, look at that. You went nice and clean. It's lovely. So you have no remainder, and that's your answer, x minus 3. So all that equals polynomial division, all it ever is just factor or simplify, right? You just express this a little different. They're the same thing. They're exactly the same thing. It's just a cosmetic change.
So sometimes when you calculus, we have to apply some consequentials to these equations. It's hard to do when it looks like this. You need a technique to make it look a little different, so it's easy to work. That's why we have this technique. This thing. So take it to calculus, you'll remember hopefully. Oh yeah. Yeah, because you gotta make it look cleaner. Because if I were to play like one for example, right? No, that won't be okay. If I play two, I get 8 minus 12 is -4. -4 plus 2, -2, -2 minus 3 is -5. So I get -5 up top and 5 down below. So I get -1. Well, if I put in 2 into here, I get -1 still, right? So that should always happen, right? This is just simplifying. That's all it is. That's it.
So it's x minus 3. Now here, for example, 6. Let's do it again. And I'm going to show you another way to do this one as well. This one's really not fun because there's so many terms. By the way, if you don't see x4, do you have to put a placeholder? Yes, please put a placeholder if you skip any terms. Likewise with synthetic division. And you don't have a constant, so you got to put 0 as well. You need placeholders for all these. Oh boy. Okay. What do you multiply 2x plus? What do you multiply 2x into 4x5? Yeah. So it comes 4x5 plus 2x4. And why do you think I'm putting a parentheses around all that? Yeah, make sure you don't mess up the arithmetic, right? Because it's -2x4 now, not positive. And then bring down the -x cubed. And you only bring one term down, the one lower. Do it again. So it should be -x3, I think. -2x4, just like old school long division, right? Oh, look at that. That came out nice. So that's 0, but then bring down the 2x squared, right? Okay. And while we're at it, we might as well bring this down as well. Now we multiply to 2x x, right? So it's 2x squared plus x. Subtract. So it's going to be very meticulous here, right? -2x. Bring down to 0 if you like. And of course, that'll be -1. So it's -2x minus 1. Subtract the sucker, you get 1. So your remainder is 1. You're going to write as +1 over 2x plus 1. So all of this is the same exact thing as the original expression.
The original expression actually is still nice. Sometimes you need to do this, especially if you're doing like limits or calculus stuff. Sometimes you need to do this. Make this easier work. Also, you do need this when you find sign asymptotes. We'll talk about that rational functions out there. Like, oh, what I approaching infinity, then I know this kind of just goes away and just put motors left. So sometimes you need that too. So, I have a question.
No, you have to write like that because we have to be precise with the algebra here. I know, yeah, that's old school. No, this is a little different now. Okay. Now I could have done this differently. I'm gonna do it off to the side here. Switch to blue. You don't have to write this down because we're gonna do this in the next few examples, but you could have done this differently. 4, 0, -1, 2. I could have done that. And when I work it out, I get this. But here's the deal.
What's the 0 of this denominator? They have, right? But technically, I did this. I pulled a 2 out of it and made x plus half. So really, I'm dividing this polynomial by x plus half, which is negative half of 0. But then afterwards, I pull that 2 out. I have to divide all my coefficients of the quotient by 2 to make it match what I got from the polynomial along with it. The remainder, don't worry about this. The remainder is divided this by, that's what I'm saying. So that's the way to achieve this synthetic division. You can kind of force the issue. But usually synthetic division is done when you divide by x plus or x minus number. But if it's linear and the coefficient is not 1, you can force the issue by pulling out that leading coefficient. So then it's x minus a or x plus a. Do the synthetic that way, but then you have to divide by that leading coefficient afterwards. Just so you know, you could do it that way. So synthetic division is still allowed for this. You just have to be a little more creative if you do it that way. So this is a nice segue to the next example, synthetic division. How does synthetic division work? I think this is much cleaner. It's actually my favorite. So this is how I usually do it. I will do, some people write like this. They'll put like the 4 here and they'll put a bunch of numbers here. It's hard to teach an old dog new tricks. So I do it like this. You put all the coefficients down. If anything skipped over, put 0 as a placeholder. And you put 4 here. This is going to be the 0 of the denominator. So we say x minus or x plus a. You put basically, you assume you're divided by x minus a. You put a. So if you see x plus 4, I put negative 4. And you just go through the motions. You bring this down, and it's basically like rinse and repeat, right? Like just a cycle. Like 4 times 5 is 20. Add up, you get 14. Rinse and repeat. 56. 56. Rinse and repeat. 232. 240. So the final answer is going to be 5x squared plus 14x plus 56 plus 232. I messed up, guys. Sorry. Okay, you still can make mistakes. So that's 224. My bad. The 232. 232 over x minus 4. Okay. And it's the same exact thing as that. It's the same exact thing. If I plug in 1 into this, I get 5 minus 6 plus 8, which is 7. Okay? So it's 97 thirds. I'm not going to do that here, but trust me, you get 97 thirds. If you plug in 1 into all this, you get 75 plus 232 over negative 3. Just trust me. Actually, that's not. It's 225. Yeah, it comes out just fine. You do get negative 7/3. Put in one in for x. That's how you can check your work. Plug in just an easy number to the original expression. Plug into the answer. They should be the same thing. Should be exactly the same thing. You can also, in Desmos or a graphing calculator, you can graph each of those. They should be the same graph. That works too. If you go y equals, y1 is the original rational expression, y2 is a quotient. They should be exactly the same thing if you graph it. So why don't you guys try example 8, see how it goes. I'll freeze the screen. Remember to skip any terms they have to skip. Very important. Here we go, guys. So yeah, you skip over x cubed with 0 placeholder, go through the motions, you get all those numbers there. So this is x cubed minus 3x squared minus x plus 1 over x plus 3. And by the way, this is what we're going to talk about Friday. It's called the remainder theorem. After negative 3 would equal 1, if fx equals the numerator. If I let fx equal the numerator, So the remainder is the same thing as f of a. F of a is the same thing as remainder. Assuming a is -3, or assume x minus a. You assume the form x minus a is anything over 3. The remainder term states that f of a equals remainder. And also, if the gives 0, then that means that this is a 0 function, or x minus a is a factor. It gives 0 as a remainder. That's also part of the factor theorem.
I've seen problems kind of like sometimes like this show up in the ACT and SAT. Sometimes they ask these kind of questions, so it shouldn't be too bad. If it's multiple choice, by the way, if these are multiple choice problems and they're asking you, hey, which of the following
Is equivalent to this. I'll just plug in a number. This multiple choice question. I'll just plug in a number to this, see what output I get. Plug in the same number to the choices and match it.
you don't even have to do syntax division on on the SAT if this multiple choice. You can always use a strategy for that one. Okay, this is our last example for today. Now let you guys get some work done. Yeah, suppose you had 8x squared minus 5 or 2x plus 1, but you really want to use synthetic division. Is there a way to do it? Yes, there is. And we already talked about it, right? 8, 0, -5, you put -half. But what you're doing is you're pulling out the 2 and making x plus half. So bring the 8 down, -4, -4, 2, -3. But divide by 2. So you get 4x minus 2. Divide by 2 except the remainder. Because the remainder is going to be divided by its own thing. So 4x minus 2 minus 3 over 2x plus 1. So you can do that. And by the way, you can always check the work by plugging a number in for x, the original, and the answers to make sure that all makes sense. Or you can set them equal to each other. If you set this equal to this, right? And multiply both sides by 2x plus 1, the left side should equal the right side. So it should all work out just fine. Okay, we'll stop there for today. Homework is just this. So it's going to be homework 3 handout, which is in your packets, your homework packets. You have 1 through 6, 7, 8, 9, 10. 8, 9, 10 is review of power functions. 7 is just more determining possible equation. Okay, here we go. We're all set. All good. Well, let me stop.